Well, working a couple of example problems now for centripetal force, centripetal acceleration. So first, let's consider a computer hard drive, and this hard drive has a disk with a radius of 2.5 inches. It spins at 5,400 revolutions per minute. So the first question to ask as we seek to calculate the centripetal acceleration: what is the velocity at the edge of this hard drive? Our centripetal acceleration is v squared divided by r, so we're going to need knowledge of the velocity. Well, we can obtain the velocity by multiplying the radius of the circle by the angular velocity. Now, angular velocity is how much angle was covered in a certain amount of time, theta divided by t, or delta theta divided by delta t if you prefer. So those are the factors that we need. And we're going to do this in the metric system. So being specified as 2.5 inches in radius, we're going to convert to centimeters, and we'll later convert to meters. But 2.5 inches times 2.54 centimeters per inch. This is our conversion factor from inches into centimeters. For the omega, 5,400 revolutions per minute. How many radians is that? One revolution is 2 pi radians. So a conversion here, 5,400 revolutions, 2 pi radians per revolution on the top. And then it's per minute, and specified. We want seconds as a more standard unit. So we convert here using the conversion factor. 1 minute is equivalent to 60 seconds. Now, you should use your calculator and see if you agree with the numbers that are being generated here. And the last conversion, 100 centimeters for 1 meter. So multiply here by 1 meter divided by 100 centimeters. And I came up with 35.9 meters per second. We're ready now to calculate the centripetal acceleration. The radius of the circle, here's our 6.35 centimeters. Again, converting that to meters. I have to shift 2 decimal places to have meters rather than centimeters. We have to square the velocity. The centripetal acceleration is v squared divided by r. And we come up with 2.03 times 10 to the 4th meters per second. There is a square here. This is meters squared per second squared. My units are not correct here. This is meters per second squared on this acceleration. That happened here when we square the velocity. Not only do we square the number, but we have to square the units. So this is meters squared divided by second squared. Then we're dividing by meters, so we get meters per second squared. And I'll see if I can ink that in here just to kind of reinforce. So meters per second squared is the unit that should be there. And then just to compare that to the acceleration due to gravity, 9.8 meters per second squared is 1 g. So we'd be looking at over 2,000 g's. You might hear g's referenced when we have talk about test pilots and flying planes. But that's the centripetal acceleration for a computer hard drive at the edge. That material has to be accelerated with 2.03 times 10 to the 4th meters per second squared. So second little example I want to do here: what's the safe speed of going around a corner, driving a car around the corner on a highway, if that corner has a radius of 250 meters, and we're given some friction coefficients. If the concrete is dry, let's say that the static coefficient of friction is 1.0 and the kinetic coefficient is 0.7. If the car wheels start sliding, we're going to have to use the kinetic coefficient of friction. If we're rolling, we use the static coefficient of friction. At any instant, the rubber on the tire is at rest with respect to the road as the tire rolls along the road. So the static coefficient is appropriate. The car has some mass m. Well, the centripetal force needed to put us around the corner would be the mass of the car times the velocity of the car squared and divide by the radius of the circle. So this is our working equation. What supplies the centripetal force? It's friction with the roadway pushing back on the car. is going to supply the centripetal force. So the force of friction supplies the centripetal force. I can write the centripetal force here as mu sub s times F sub n. And we're taking the maximum value of the static friction force, the maximum available, would be mu sub s times F sub n, the normal force. The normal force, we're on a flat roadway, so mg is our normal force. Mg is the weight going down. The roadway pushes back up on the car with the normal force, which is equal to mg. We're not accelerating up or down off the roadway. So there's a balance in the vertical forces. The normal force equals mg. So this F sub c then is our calculation of mu sub s times m times g. And we have the coefficient of friction, 1, times the mass of the car, times 9.8. Again, m and 9.8 give us the normal force. Now here is our expression for the centripetal force, mass of the car, velocity squared divided by the radius of our circle. Notice that the mass cancels off. This is nice that the universe works this way. So highway engineers can build curves that work for Cadillacs or work for Volkswagens. The mass of the car does not matter. The same posted speed limit for the curve works for both cars, both vehicles, assuming they both have coefficient of friction of 1.0 for their tires on the road. Well, we're ready to solve here. So we can multiply both sides by the 250 and obtain a value for v squared. We take a square root. We find 49.5 meters per second. Doesn't mean a lot to us in the United States, so let's convert it to miles per hour. So 49.5 times 1 divided by 0.447 gives us this speed. Do not try to verify this calculation with the car, but that's the maximum speed that theoretically we could go around the curve with the given parameters. So keep practicing.